USB 1.0, 1996. USB 1.0 was the first official version of the Universal Serial Bus Standard introduced in 1996. Its purpose was to replace the many different connectors and ports on personal computers with a single standardized interface. USB 1.0 supported two speeds: low speed, which operated at 1.5 megabits per second, primarily used for keyboards, mice, and simple peripherals, and full speed, which ran at 12 megabits per second, capable of handling devices like printers and early storage drives. This version introduced the standard USB-A and USB-B connectors, the 4-pin design, and the concept of plug-and-play, meaning devices could be connected without restarting the computer. Despite its innovation, USB 1.0 had limited adoption at first because of compatibility issues and the slow speed compared to parallel and serial ports already in use. USB 1.1, 1998. USB 1.1 addressed the problems of the original USB 1.0 standard. Released in 1998, it fixed compatibility issues that caused devices to fail to connect properly and clarified electrical specifications. USB 1.1 maintained the same data rates of low speed at 1.5 megabits per second and full speed at 12 megabits per second. The update ensured wider adoption across computers, printers, scanners, and early storage devices. It also standardized device classes such as Human Interface Devices, HID, which include keyboards and mice, making it easier for operating systems to support peripherals without custom drivers. USB 1.1's improvements established USB as a reliable interface for everyday computing, setting the stage for the next major speed jump. USB 2.0, 2000. Released in 2000, USB 2.0 introduced high speed, a significant increase to 480 megabits per second, roughly 40 times faster than USB 1.1 full speed. USB 2.0 maintained backward compatibility, so older USB 1.x devices could still function in the new ports, although at the lower speed. This version became the standard for nearly a decade due to its reliability and speed. USB 2.0 supported a wide range of devices, including external hard drives, cameras, flash drives, and game controllers. It also improved power delivery, allowing devices to draw more current, up to 500 milliamps per port, which enabled small devices like smartphones and MP3 players to charge through USB. USB 3.0, 2008. USB 3.0, released in 2008, brought a major speed upgrade to 5 gigabits per second, a rate labeled as super speed. This version introduced a new set of connectors with additional pins, typically recognized by blue-colored ports, and maintained backward compatibility with USB 2.0 devices. USB 3.0 included improvements in data transfer efficiency, using a new dual-simplex architecture which allows data to flow in both directions simultaneously, rather than alternating as in previous USB versions. The standard also increased power output to 900 milliamps, enabling faster charging for larger devices like tablets. These changes made USB 3.0 ideal for high-bandwidth applications such as external SSDs, HD webcams, and fast data backup drives. USB 3.1, 2013. USB 3.1, introduced in 2013, doubled the speed of USB 3.0 to 10 gigabits per second, a standard referred to as Super Speed Plus. USB 3.1 also introduced improvements in power delivery, supporting up to 100 watts through USB power delivery, which allowed not just charging, but powering devices like laptops directly from USB ports. This version included refinements to the physical interface and signaling to improve efficiency and reliability. USB 3.1 ports are often compatible with the USB-C connector type, which is reversible and can be plugged in either way, making it more user-friendly. The combination of high-speed transfer and increased power delivery made USB 3.1 suitable for external displays, high-speed storage, and professional peripherals. USB 3.2, 2017. USB 3.2, released in 2017, introduced multiple modes and further increased maximum speeds, creating some confusion in naming. It supports two-lane operation over USB-C cables, allowing speeds up to 20 gigabits per second. Essentially, USB 3.2 is a refinement of USB 3.1, offering better performance when using compatible USB-C cables and devices. The standard maintains backward compatibility with USB 3.0 and USB 2.0, so older devices continue to function at their respective speeds. USB 3.2 also enhanced data encoding, making transfers more efficient and reducing overhead. This version was largely focused on high-performance storage solutions, external GPUs, and displays, benefiting users who need maximum throughput for large files or high-resolution video streams. USB 4, 2019. USB 4, introduced in 2019, is based on the Thunderbolt 3 protocol and standardizes high-speed data transfer across devices. It supports speeds up to 40 gigabits per second and requires USB-C connectors, eliminating older USB-A ports for this standard. USB 4 simplifies the ecosystem by combining data, video, and power delivery into a single protocol. Devices can negotiate bandwidth dynamically, prioritizing video over data when needed, making it ideal for external monitors, docking stations, and high-performance storage. The standard also ensures full backward compatibility with USB 3.x and USB 2.0 devices, while providing significant improvements in efficiency and versatility. USB 4 v 2.0, 2022. USB 4 version 2.0, released in 2022, doubles the maximum data transfer speed of USB 4 to 80 gigabits per second when using high-quality cables. This version continues to use USB-C connectors exclusively and maintains backward compatibility with USB 4, USB 3.x, and USB 2.0 devices. USB 4 v 2.0 improves data and video multiplexing, allowing devices to dynamically allocate bandwidth between multiple streams, such as external displays and storage, more efficiently than previous versions. The update also simplifies the USB naming conventions, though users must still ensure they use certified cables to achieve the maximum speed. With its ultra-high speed and versatility, USB 4 v 2.0 is positioned as the future standard for laptops, docking stations, external SSDs, and high-resolution displays, enabling faster workflows and more reliable connectivity across a broad range of devices. Bluetooth. Bluetooth is a short-range wireless technology that lets devices communicate with each other over distances up to 10 meters, sometimes more. It uses radio waves in the 2.4 GHz band to send small packets of data back and forth between devices. You've seen Bluetooth in action if you've ever paired wireless earbuds with your phone, connected a wireless game controller to a console, or transferred files between two smartphones. Bluetooth uses a process called pairing, which creates a secure, one-to-one connection between two devices. Once paired, they remember each other and can reconnect automatically in the future. Most modern Bluetooth uses something called Bluetooth Low Energy, or BLE. BLE consumes much less power, making it ideal for smartwatches, fitness trackers, or wireless keyboards that run on small batteries. However, Bluetooth isn't meant for large data transfers, just short bursts of information like audio signals, input commands, or sensor data. The downside? Interference. Bluetooth operates in the same frequency range as Wi-Fi and microwave ovens. That's why sometimes your audio crackles when you're cooking while listening to a podcast. NFC. NFC stands for Near Field Communication. It's a type of wireless communication that only works over extremely short distances, typically 4 centimeters or less. It's based on older RFID technology and is designed for fast, simple interactions between devices that are physically close. You've used NFC if you've tapped your phone on a payment terminal, scanned a travel card at a subway gate, or exchanged contact info with another phone just by placing them back to back. NFC doesn't require pairing. one device sends a signal, and the other receives it instantly. It's almost like whispering directly into another device's ear. There are two types of NFC modes: active and passive. In active mode, both devices generate their own radio frequency field. In passive mode, only one device actively transmits, and the other just listens, like an NFC tag that opens a website or Wi-Fi menu when tapped. Because it's so short range, NFC is actually more secure than many other wireless methods. Someone trying to intercept an NFC transaction would have to be standing uncomfortably close, like right next to you. That makes it useful for contactless payments, digital ID cards, and secure authentication. Infrared (IR). Infrared communication uses invisible light instead of radio waves. It was one of the earliest forms of wireless data transfer in consumer devices. You've seen IR in your TV remote. When you press a button, it sends a beam of infrared light to the TV, which receives the signal and performs the command. Infrared requires line of sight. That means the two devices need to be pointed directly at each other, with no obstacles in between. It's directional, like shining a flashlight. This makes IR very limited in range, usually less than 5 meters, and vulnerable to interference from sunlight or other bright light sources. In the early 2000s, infrared was also used to transfer files between mobile phones, but it was painfully slow and clunky. Today, IR is mostly used for remote controls, air conditioner panels, and other low-bandwidth, single-function devices. The advantage of IR is that it's cheap, easy to implement, and doesn't suffer from radio interference, but it's being replaced by more flexible options like Bluetooth and Wi-Fi in most modern gadgets. Zigbee. Zigbee is a wireless communication protocol designed specifically for smart home devices and low-power IoT systems. It's optimized for sending small amounts of data over long periods without draining battery life. Zigbee operates in the same 2.4 GHz band as Bluetooth, but uses a mesh network structure. In a Zigbee mesh network, each device, like a smart bulb, sensor, or plug, can relay signals from other devices. So instead of each device needing a direct connection to your central hub or router, the signal can hop from one device to the next until it reaches its destination. This extends the coverage and increases the reliability of the entire network. For example, if your smart thermostat is too far from the main hub, the signal might bounce through a smart plug in the hallway and then a light switch in the kitchen to reach the thermostat. That's the mesh at work. Zigbee's strengths are its low power usage and scalability. You can have dozens of devices communicating efficiently without crowding your main Wi-Fi. But Zigbee requires a dedicated hub, like a smart home controller, to manage the devices. And since different manufacturers sometimes implement Zigbee slightly differently, not every device works with every hub out of the box. Z-Wave. Z-Wave is similar to Zigbee but uses a different frequency, typically 908 MHz in the US. This means it avoids interference with Wi-Fi and Bluetooth, which operate at 2.4 GHz. Like Zigbee, Z-Wave is designed for smart home automation and low-bandwidth device communication. It also uses a mesh network, where each device can pass along messages to extend the signal range. Z-Wave has slightly longer range per device, up to 100 meters in open air, and can support up to 232 devices in a single network. It's known for strong interoperability. Z-Wave devices must meet strict standards, so a Z-Wave motion sensor from one brand can work with a Z-Wave hub from another. That's not always true with Zigbee. However, Z-Wave networks are a bit slower than Zigbee and can be more expensive due to licensing fees. Still, many professional smart home systems rely on Z-Wave for stability and long-term performance. Z-Wave and Zigbee don't compete directly with Wi-Fi. Instead, they complement it by handling background tasks like monitoring doors, adjusting lights, or triggering alarms, while Wi-Fi deals with video streaming and internet browsing. Wi-Fi. Wi-Fi is the most common wireless technology used to connect devices to the internet without physical cables. It transmits data using radio waves in two frequency bands, 2.4 GHz and 5 GHz. The 2.4 GHz band offers wider coverage but slower speeds. The 5 GHz band is faster but has a shorter range and doesn't pass through walls as easily. When you connect your phone or laptop to Wi-Fi, you're joining a local wireless network, typically managed by a router. That router acts like a traffic controller, directing collecting data between your device and your internet service provider. Most modern routers also support dual-band or tri-band Wi-Fi. Wi-Fi standards are labeled by numbers like 802.11n, 802.11ac, and 802.11ax. The most recent version is called Wi-Fi 6, 802.11ax, which improves speed, range, and the ability to manage many devices at once, perfect for busy homes with smart TVs, game consoles, and smart home devices all connected. One important thing, Wi-Fi is fast, but it's also vulnerable. If your network isn't secured with a strong password and encryption like WPA3, outsiders can connect to your network and potentially access your data. Li-Fi. Li-Fi stands for light fidelity. Unlike Wi-Fi, which uses radio waves, Li-Fi uses visible light to transmit data. It works by rapidly modulating the brightness of LED lights in a way that's invisible to the human eye. A Li-Fi-enabled device picks up these changes using a photodetector and decodes the data. Li-Fi is incredibly fast. In lab tests, it has reached speeds over 200 gigabits per second. That's faster than most fiber optic internet connections. But it also has limitations. Since it uses light, it can't pass through walls or work in complete darkness. It also requires a direct line of sight between the transmitter, the light source, and the receiver, your device. Still, Li-Fi is promising for certain environments, like hospitals, where radio waves might interfere with sensitive equipment, or on airplanes, where it could reduce network interference. In homes and offices, Li-Fi could complement Wi-Fi in specific rooms where ultra-fast and secure communication is needed. Cellular networks, 3G, 4G, 5G. Cellular networks use radio towers to provide wireless coverage across large geographic areas. Your phone connects to the nearest cell tower, which then routes calls, messages, and internet traffic to and from your device. Each generation of mobile technology has improved speed, capacity, and latency. 3G was the first network fast enough for mobile internet browsing and video calling. 4G brought speeds fast enough for HD video streaming, mobile gaming, and high-speed downloads. It uses technologies like LTE, long-term evolution, to achieve this. 5G is the current generation, ultra-low latency, and the ability to connect more devices at once. It uses a mix of low-band, mid-band, and high-band frequencies. High-band 5G, known as millimeter wave, can deliver gigabit-per-second speeds, but only over short distances and with clear line of sight. 5G opens the door to applications like autonomous vehicles, remote surgeries, real-time augmented reality, and ultra-dense IoT networks in smart cities. However, it also requires a dense infrastructure of small cell towers, especially in urban environments. Satellite Internet. Satellite internet connects you to the web using satellites orbiting Earth. It's ideal for rural or remote areas where fiber or cable lines don't reach. Traditional satellite systems use geostationary satellites positioned around 35,000 kilometers above the Earth. These systems have global coverage, but because the signal has to travel so far, they suffer from high latency, usually over 600 milliseconds. This delay can be noticeable in online gaming or video calls. Download speeds are typically slower, and upload speeds even more limited. Data caps and higher costs are also common. A newer generation of satellite internet, like Starlink by SpaceX, uses low Earth orbit (LEO) satellites, which orbit at around 500 to 2,000 kilometers. Because the signal travels a shorter distance, latency drops significantly, often below 50 milliseconds. LEO satellite constellations can provide high-speed internet to previously underserved areas, but they require thousands of satellites working together and constant tracking to maintain coverage. UWB Ultra-Wideband. Ultra-Wideband is a short-range, high-frequency wireless technology used for precise location tracking and fast data transmission over short distances. It operates by sending very short pulses of radio energy across a wide frequency spectrum, typically several gigahertz wide. This makes it resistant to interference and capable of pinpoint accuracy. UWB isn't designed for internet access. Instead, it's used for spatial awareness. For example, Apple's AirTags use UWB to help iPhones precisely locate them, even showing directional arrows as you walk closer. Some high-end smart home devices use UWB for presence detection, like turning on lights when someone enters a room or unlocking a car door when the owner is nearby. Because it can detect movement with sub-centimeter accuracy and doesn't require pairing like Bluetooth, UWB is ideal for secure authentication, hands-free control, and indoor navigation. It's not widely used yet, but as smartphones and wearables continue adopting UWB chips, you'll see more devices using it for advanced motion and positioning features. Wireless charging. Wireless charging uses a process called inductive charging to transfer power from a charging pad to a device without needing a physical cable. It works using two coils, one inside the charger and one inside the device. When the charger's coil is energized, it creates a magnetic field. The device's coil picks up that field and converts it into electricity. This only works over very short distances, usually less than 10 millimeters, which is why your phone has to sit directly on the pad. The most common standard is Qi, pronounced Qi, which is supported by most modern smartphones, wireless earbuds, and even electric toothbrushes. There are also resonant and radio frequency charging technologies that allow for slightly more distance, but they're less common in consumer products. Wireless charging is convenient, but it's generally slower and less efficient than plugging in directly. More heat is generated, and positioning matters. If your phone isn't aligned properly, it might charge slowly or not at all. Still, it's ideal for nightstands, desks, or car mounts, where you want to avoid plugging and unplugging your device multiple times a day. SSL. SSL stands for Secure Sockets Layer. It was one of the first major protocols used to secure data sent between two computers, like your browser and a website. Let's say you're buying shoes online. When you enter your credit card number, SSL creates a kind of encrypted tunnel so no one can spy on that info as it travels. It scrambles the data into a secret code using what's called a symmetric key, which only the website and your browser know. But here's the thing, SSL is pretty old. And even though the lock icon on your browser still says SSL, what's actually being used today is something newer. TLS. TLS stands for Transport Layer Security. It's the modern, upgraded version of SSL. When you see a URL starting with HTTPS, that's TLS at work. It not only encrypts your messages, but it also verifies that the server you're talking to is real, not a fake website pretending to be Amazon or your bank. TLS uses a mix of symmetric and asymmetric encryption. That means it starts by using a public key to exchange a secret, then switches to faster symmetric encryption once the connection is safe. And just so you know, we're now on TLS version 1.3, which is faster and more secure than anything before. SSH. SSH stands for Secure Shell. It's what developers use when they need to remotely log into a server, like connecting to a computer in another country to run commands. Imagine a hacker trying to sniff your password while you type it into a login screen. SSH stops that. It encrypts everything. The commands, the data, even your keystrokes. SSH keys are like digital locks and keys. You install a public key on the server, and your private key stays with you. If the keys match, you're in. Otherwise, no entry. That's why SSH is also used for secure file transfers using SFTP. IPsec. IPsec, or Internet Protocol Security, works at the IP layer. That's the part of the Internet that moves data from one address to another. Think of it like putting your letter inside a secure envelope before dropping it in the mailbox. IPsec adds encryption and integrity checks directly to the data packets. It's often used in VPNs to make sure nobody can read or tamper with your traffic while it travels across public networks. It can work in two modes. Transport mode protects just the message, while tunnel mode protects the entire packet. Tunnel mode is what VPNs usually use. WPA3. WPA3 is the latest Wi-Fi security protocol. It stands for Wi-Fi Protected Access 3. You've probably seen WPA2 on your home router before, but WPA3 makes things even tougher for hackers. With WPA3, even if someone tries to guess your password over and over, the system makes it painfully slow, thanks to something called SAE, or Simultaneous Authentication of Equals. Also, WPA3 uses forward secrecy. That means even if someone gets your Wi-Fi password later, they still can't go back and decrypt your old data. It's like changing the lock every time someone leaves the room. DNSSEC. DNSSEC stands for Domain Name System Security Extensions. Normally, when you type a website name like example.com, your computer asks a DNS server for the actual IP address. But attackers can spoof those replies, redirecting you to fake sites. DNSSEC fixes that by adding digital signatures to DNS records. So now, your computer can verify that the IP address really came from a trusted source, not a hacker. It's like checking the seal on a medicine bottle. If the seal's broken or missing, you don't trust what's inside. HTTPS. HTTPS stands for Hypertext Transfer Protocol Secure. It's basically the secure version of HTTP, the protocol that loads web pages. When you visit a website with HTTPS, all communication between your browser and the site is encrypted using TLS. So if you're submitting a contact form, logging in, or shopping online, HTTPS makes sure nobody can read or change that data in transit. Without HTTPS, anything you send could be intercepted or modified by someone in between, like a rogue Wi-Fi hotspot at a coffee shop. That's why modern browsers now mark non-HTTPS sites as not secure. SFTP. SFTP means Secure File Transfer Protocol. It's not the same as FTP over SSL, which is called FTPS. SFTP runs on top of SSH, so it's got that built-in encryption and authentication. You can think of SFTP like sending files through a locked armored tunnel. It's commonly used by companies and developers to upload and download files securely from remote servers. Since it uses SSH, it also supports things like key-based authentication, meaning you don't have to send your password every time. That's safer, and it reduces the risk of brute force attacks. Radius. Radius stands for Remote Authentication Dial-In User Service. It's a protocol used to manage authentication, authorization, and accounting, often called AAA, for users accessing a network. Imagine a university with hundreds of students logging into Wi-Fi across campus. Instead of checking usernames and passwords on each device, the network sends those credentials to a central Radius server. That server says yes or no, keeps logs of who connected, and applies specific rules, like limiting access to certain resources. It also supports two-factor authentication, which adds another layer of protection. Kerberos. Kerberos is a network authentication protocol that uses tickets instead of passwords. It was originally developed at MIT and is widely used in enterprise environments, especially in Windows domains. When you log into your computer, Kerberos doesn't keep asking for your password for every service. Instead, it gives you a time-limited ticket-granting ticket, TGT. Think of it like an all-access pass. When you try to access the printer or shared drive, your system presents that ticket, and if it's still valid, you're in. It reduces the chances of your password being intercepted, since it's not reused constantly. OAuth 2.0. OAuth 2.0 is a token-based authorization protocol. You've probably used it without realizing, like when you click Sign in with Google on a new app. Instead of giving the app your actual password, OAuth hands it a limited access token. That token says what the app can do, like read your email, but not send any. And if something goes wrong, the token can be revoked without affecting your main account. OAuth separates the roles of authentication and authorization, which makes it safer when used correctly. It's a major part of how modern web services connect securely. OpenVPN. OpenVPN is an open-source VPN protocol that uses SSL/TLS to establish secure point-to-point or site-to-site connections. It's highly configurable and works on many platforms, which is why it's widely adopted by both individuals and corporations. When you connect using OpenVPN, your internet traffic is encrypted and routed through a secure tunnel to a remote server. That server becomes your new IP address, masking your real location. OpenVPN can use either UDP for speed or TCP for reliability, depending on what you need. It's especially popular for bypassing censorship, accessing restricted content, and securing public Wi-Fi usage. WireGuard. WireGuard is a newer VPN protocol designed to be faster, simpler, and more secure than older ones like IPsec and OpenVPN. It uses state-of-the-art cryptography and has just a few thousand lines of code compared to hundreds of thousands in traditional VPN protocols. That means it's easier to audit and less prone to bugs or vulnerabilities. When you use WireGuard, it creates a secure peer-to-peer tunnel between two devices. It's lightweight enough to run smoothly on phones, routers, or even small IoT devices. And because of its speed and security, many VPN providers are now switching to it. 802.1x. 802.1x is a standard for controlling access to a network based on authentication. It's often used in enterprise Wi-Fi setups and wired Ethernet ports. When you plug in or connect to the Wi-Fi, 802.1x steps in to check if you're allowed in. It usually works with Radius and can use certificates or usernames and passwords to validate users. If you're not authenticated, you're blocked before you even get an IP address. This keeps unauthorized devices off the network entirely. Think of it like needing a keycard just to open the building door, not just to access individual rooms. MACsec. MACsec stands for Media Access Control Security. It's a Layer 2 protocol that encrypts traffic on Ethernet links, basically the cables that connect devices on a LAN. While TLS protects data between apps and IPsec protects IP packets, MACsec secures everything directly on the physical link. This is important in high-security environments like government facilities or data centers. MACsec ensures that even if someone physically taps into the network cable, all they get is scrambled noise. device. It also verifies the identity of connected devices, preventing rogue hardware from silently joining the network. PGP, or Pretty Good Privacy, is used to secure emails and files. It combines both symmetric and asymmetric encryption. When you want to send someone a private message, you use their public key to encrypt it, and only their private key can unlock it. The message is also signed with your private key, so they can verify that it came from you. PGP is decentralized, meaning there's no central authority. You manage your own keys. It's commonly used by journalists, whistleblowers, and anyone who needs strong privacy without relying on third-party services. LDAP over SSL, LDAPS. LDAP stands for Lightweight Directory Access Protocol. It's used to access and manage directory information like usernames, passwords, email addresses, and organizational roles. But standard LDAP doesn't encrypt traffic. That's where LDAPS comes in. It wraps LDAP in SSL or TLS to secure the connection. For example, when your computer checks with the corporate directory to see if your login is valid, LDAPS ensures nobody can eavesdrop or tamper with that exchange. It's often used with Microsoft Active Directory in enterprise networks to manage employee logins securely. SMIME. SMIME stands for Secure Multipurpose Internet Mail Extensions. It's used to encrypt and digitally sign email messages. When someone sends you an email with SMIME, it uses their certificate to prove that the message really came from them and that it wasn't changed in transit. You can also encrypt your reply so only they can read it. SMIME is widely used in business and government because it integrates easily into tools like Microsoft Outlook or Apple Mail. But it relies on certificate authorities (CAs), which can introduce complexity in setup and key management. Zero Trust Protocols. Zero Trust is a security philosophy that's now being applied in protocol design. It assumes no device or user should be trusted by default, even inside the network. Protocols supporting Zero Trust enforce continuous verification. That includes multi-factor authentication, device posture checks, and behavioral analytics. For example, instead of just checking credentials when a user logs in at 9 a.m., a Zero Trust protocol might keep verifying every few minutes. If your device location suddenly changes or a file transfer looks suspicious, it can cut access immediately. The goal is to limit lateral movement and reduce the blast radius of an attack. DTLS. DTLS stands for Datagram Transport Layer Security. It's basically TLS adapted for use with UDP instead of TCP. Since UDP is used in real-time applications like video calls and online gaming, DTLS brings encryption to those without introducing too much latency. Imagine having a secure video chat where every packet of data is encrypted, without the delays that would normally come from handshakes or retransmissions. DTLS is used in applications like WebRTC and VPNs that need speed and security at the same time. QUIC. QUIC stands for Quick UDP Internet Connections. Developed by Google, it's a transport layer protocol that combines the benefits of TCP, TLS, and HTTP2 all over UDP. It improves connection setup times, handles packet loss better, and provides built-in encryption. QUIC is used by major services like YouTube and Google Search. With QUIC, if you reload a web page or switch from Wi-Fi to mobile data, the connection stays up. It was designed to make secure web communication faster and smoother, especially on mobile networks. USB stands for Universal Serial Bus. It connects devices like keyboards, mice, printers, drives, and phones. The most recognizable version is USB Type-A, rectangular, one-sided, and present on most older computers. USB 2.0 offers speeds up to 480 megabits per second. USB 3.0 increases that to 5 gigabits per second and includes a blue insert. USB 3.1 and 3.2 support 10 and 20 gigabits per second, respectively. All versions are backward compatible, but the speed is limited by the oldest device in the chain. USB Type-C is smaller, oval-shaped, and reversible. It handles data transfer, video output, and power delivery, all at once. Many modern laptops and phones use USB-C instead of traditional power or video ports. When paired with USB 3.2 or USB 4, it can support up to 40 gigabits per second. Some USB-C ports also support Thunderbolt, which expands capability further. HDMI stands for High Definition Multimedia Interface. It sends digital video and audio through one cable. It's used to connect to monitors, TVs, and projectors. HDMI 1.4 supports 4K at 30 Hz. HDMI 2.0 raises that to 4K at 60 Hz. HDMI 2.1 increases bandwidth to 48 gigabits per second, enabling 8K or 4K at 120 Hz. The connector is wide and trapezoid-shaped. Mini and micro HDMI are smaller versions used on tablets and compact devices. DisplayPort also sends digital video and audio. It supports higher bandwidth than HDMI and can drive multiple monitors from one port. DisplayPort 1.2 supports 4K at 60 Hz. Version 1.4 allows 8K. DisplayPort 2.0 supports up to 16K or two 8K monitors. The connector is rectangular with one notched corner. DisplayPort allows daisy chaining monitors. HDMI does not. Some USB-C ports support DisplayPort Alt mode, which allows video output through adapters. Ethernet, or RJ45, connects computers to wired networks. It's wider than a phone jack and has 8 metal contacts. It supports faster and more stable internet than Wi-Fi. Fast Ethernet delivers 100 megabits per second. Gigabit Ethernet supports 1 gigabit per second. Higher speed versions like 2.5G, 5G, and 10G require newer cables and network equipment. Wired Ethernet is used for gaming, video streaming, and professional work where latency matters. Audio jacks transmit analog sound signals between devices. The most common type is the 3.5mm jack, also known as a headphone jack. It connects headphones, microphones, and speakers to a computer. There are two main variants: TRS, tip ring sleeve, and TRRS, tip ring sleeve. TRS has 3 contact points and supports stereo audio. TRRS adds a 4th contact, enabling both stereo audio and microphone input in a single plug, commonly used in headsets. Older computers sometimes include separate jacks for microphone input and speaker output, typically color-coded pink and green. Newer devices often combine both into one jack using TRRS. The jack provides analog sound, which means it can degrade with interference or cable quality. USB or digital audio interfaces provide cleaner signals but require different ports. Thunderbolt ports are high-speed connections developed by Intel, often found in high-end laptops and desktops. Thunderbolt 1 and 2 use the same connector as Mini DisplayPort, while Thunderbolt 3 and 4 use USB-C. Thunderbolt 3 supports up to 40 gigabits per second and allows for data, video, and power simultaneously. It can connect to high-speed storage devices, 4K or 5K displays, and external GPUs. Thunderbolt 4 has the same speed but requires stricter specifications, including support for two 4K displays and PCIe at 32 gigabits per second. Thunderbolt ports are backward compatible with USB-C, but not all USB-C ports support Thunderbolt. Devices and cables must be certified for full Thunderbolt performance. Look for the lightning bolt icon near the port to confirm Thunderbolt support. SD card slots allow direct access to memory cards used in cameras, phones, and other devices. Full-sized SD card slots accept standard secure digital cards, while some laptops use micro SD slots for smaller cards. These ports are used to read or write data, often photos or video files. SD cards come in formats like SD, SDHC, and SDXC, with speeds and capacities varying accordingly. A UHSI slot supports up to 104 megabytes per second, while UHS-2 and UHS-3 support faster transfer rates, mainly for professional use. VGA ports are analog video connectors, once standard on older computers and monitors. VGA stands for Video Graphics Array. It has 15 pins arranged in 3 rows and typically has a blue color. VGA transmits only video, not audio. It supports resolutions up to 1080p, but lacks sharpness compared to digital ports like HDMI or DisplayPort. Signal quality can degrade over long cables or with interference. VGA is largely obsolete, but may still appear on legacy hardware or projectors. DVI, or Digital Visual Interface, is another video port developed to improve on VGA. It comes in several types: DVI-D, digital only, DVI-A, analog, and DVI-I, integrated digital and analog. DVI supports higher resolutions and better image quality than VGA. It does not carry audio, only video. Dual-link DVI supports resolutions up to 2560 by 1600. Like VGA, DVI has been mostly replaced by HDMI and DisplayPort, but can still be found on older monitors and graphics cards. eSATA, or external SATA, is a port designed to connect external hard drives using the same protocol as internal SATA drives. It provides faster data transfer than USB 2.0, but has mostly fallen out of favor with the rise of USB 3.0 and Thunderbolt. Unlike USB, eSATA does not supply power. Devices need their own power source. It uses a distinct flat, narrow connector, similar to internal SATA ports, but slightly modified for external use. eSATA was primarily used for professional storage setups, but is now rarely included in modern computers. FireWire, also known as IEE-1394, was developed by Apple for high-speed data transfer. It appeared on many Macs and some PCs in the early 2000s. FireWire 400 supported 400 megabits per second, while FireWire 800 doubled that speed. It was used to connect camcorders, external drives, and audio interfaces. Unlike USB, FireWire allowed peer-to-peer data transfers without a computer acting as a host. This made it popular for video editing workflows. FireWire has since been phased out and replaced by USB and Thunderbolt. PS2 ports are round connectors used for connecting keyboards and mice. They were color-coded, purple for keyboard, green for mouse. PS2 allows direct communication with the motherboard, avoiding some of the latency or polling delays seen in USB. Some business systems still include PS2 for compatibility with older peripherals, but it's rare on consumer hardware today. Unlike USB, PS2 does not support hot plugging. Devices must be connected before the computer boots. Serial ports, also known as COM ports, use 9-pin or 25-pin connectors. They transmit data 1 bit at a time and were once common for mice, modems, and industrial equipment. Most consumer computers no longer include serial ports, but they remain in use for point-of-sale systems, networking hardware, and embedded devices. Serial ports are often replaced by USB to serial adapters for compatibility with modern systems. Parallel ports are wider, with 25 pins, and were traditionally used to connect printers. Like serial ports, they transmit data, but in multiple channels simultaneously. These ports are obsolete in modern consumer hardware and have been replaced by USB. However, they may still be used in legacy industrial systems or specialty hardware where USB compatibility is not available. Kensington lock slots are not data ports, but they are worth noting. They're small rectangular holes usually located on laptops or monitors. A Kensington lock is a physical security device, a metal cable and lock that prevents theft of hardware. These locks are common in schools, libraries, and public workstations where unattended devices need to be secured. Docking connectors are proprietary ports used to attach a laptop to a docking station. The docking station expands connectivity by providing extra USB ports, video outputs, Ethernet, and charging through one physical link. Older laptops had dedicated docking connectors on the underside. Modern setups often use USB-C or Thunderbolt ports for docking, eliminating the need for special hardware connectors. Combo audio-video ports are becoming more common on compact laptops and tablets. These may look like a standard 3.5mm headphone jack, but support both audio input and output, or video output, through adapters. Some USB-C ports support audio, video, data, and charging all at once, depending on the device's internal configuration. This consolidation reduces the number of ports needed, but requires compatible accessories. MagSafe is a magnetic power connector originally developed by Apple. It snaps into place for charging and disconnects safely if pulled, preventing a laptop from being dragged off a desk. The original MagSafe used a T-shaped or L-shaped magnetic connector. Apple phased it out in favor of USB-C charging, but later reintroduced a new version called MagSafe 3 for modern MacBooks. MagSafe provides dedicated charging, leaving USB-C ports free for data and video. DC-in ports are circular power connectors used on many Windows laptops. They deliver power from an AC adapter to the internal battery. The size and voltage of DC-in ports vary by manufacturer, making them non-interchangeable. These ports are typically used only for power and offer no data or video functionality. Mini DisplayPort is a smaller version of DisplayPort. It was used on older MacBooks and Microsoft Surface devices. Like full-size DisplayPort, it supports high resolutions and audio. Mini DisplayPort can be adapted to HDMI, VGA, or DVI. It has largely been replaced by USB-C and Thunderbolt in newer machines. SPDIF ports transmit digital audio using either coaxial cables with RCA connectors or optical cables OSLINK. These ports are used to connect high-end speakers, home theater systems, and digital audio equipment. SPDIF supports multi-channel surround sound formats like Dolby Digital and DTS. It delivers cleaner audio than analog jacks, with less interference, but does not support the newest high bitrate audio formats like HDMI does. Smart card readers are ports used mainly in enterprise environments. They accept credit card-sized security cards with embedded chips, often for user authentication or secure login. These ports are common in government or corporate-issued laptops. Some also support contactless smart cards, depending on the reader. SIM card slots appear on laptops and tablets that support cellular connectivity. A SIM card allows the device to access mobile data networks similar to a smartphone. These are typically nano SIM trays and are located on the side or back of the device. Paired with an internal LTE or 5G modem, a SIM slot enables always-on internet access without Wi-Fi. IR blasters, or infrared ports, were once found on laptops and phones for remote control functions. They emit infrared signals used to control TVs, set-top boxes, or projectors. IR has largely disappeared from laptops, but still exists in some smartphones or specialized control devices. Line-in and line-out jacks are separate from standard headphone or mic jacks. Line-in is used to input audio from another device, such as a mixer, amplifier, or media player. Line-out sends audio to external speakers or recording gear. These jacks are common on desktops or professional audio equipment and use the same 3.5mm connectors, but are optimized for higher fidelity signal handling. Combo ports like USB-C with DisplayPort, Thunderbolt, charging, and audio in one connector are now standard on many laptops. They reduce the number of physical ports but require understanding compatibility. Not all USB-C ports are created equal. Some only do data, others do charging or video, and only a few do everything. Checking the symbols beside the port helps. A lightning bolt for Thunderbolt, a battery for charging, or a D for DisplayPort.